Section 3.2, 3 topics today. Topic 1, derivative is a function. Topic 2, other derivative notation. Topic 3, more examples. Take a review about what we learned in the last class. Review number 1. What is a derivative? Derivative is a limit, a special limit. Because a limit of this form has many applications. We give the limit a special name, derivative, and a special notation. Review number 2. Computing a derivative. This process is called a differentiation. If the limit exists, if this limit exists, we know that a limit may or may not exist. When x approaches the point A, if this guy approaches more than one number, then the limit doesn't exist. If the limit exists, we say that the function f is differentiable at the point A. Differentiable means the derivative is computable. Otherwise, if the limit doesn't exist, we say that the function f is non-differentiable at the point A. Non-differentiable, the derivative is not computable at the point A. Review number 3. Derivative at the point A is the slope of the tangent line to the graph of the function at this point. This point, the x-coordinate is A. Suppose this curve is the graph of the function f. Point A is on the curve. At this point, there is a tangent line. The slope of this tangent line is derivative of the function at the point A. Now, topic 1. Derivative is a function. Each of these two formulas is called the definition of derivative. The definition says that derivative is a limit. In these two formulas, the point A is a constant. If we replace the point A by a variable, say by x, then derivative becomes a function of x. In this equation, replace the point A by x, then we have this equation. This equation says that derivative of the function f at x is this limit. Because this equation already has the variable x, before we replace the point A by x, we need to change x to some other letter, say to t. Now, in this limit, replace A by x, then we have this equation. This is one example about how to use these two formulas. Let function f be 1 over x. Find derivative at x. Then determine an equation of the line tangent to the graph of the function at this point. we have two formulas to compute the derivative. Let me pick this formula. By this formula, I have this equation. F of t, plug in t in the x here, then f of t is 1 over t. So 1 over t here. Minus f of x is 1 over x. In this limit, x is fixed. T is approaching x. To find this limit, I can use direct substitution. Plug in x in t. Then 1 over x minus 1 over x is 0. X minus x is 0. So if I plug in x in t, then I will get 0 over 0. I cannot tell the limit. To find this limit, we need to simplify the function. Because the numerator is a fraction minus a fraction, I want to use common denominator to simplify the function. Rewrite the first term 1 over t as x over t times x. The second term 1 over x as t over t times x. Then the two terms have the same denominator, and I can combine them to get this equation. Rewrite this fraction as this fraction times 1 over t minus x. And take out the negative sign from x minus t to get this equation. Cancel t minus x from the top and from the bottom. Then we have this equation. Now, to find this limit, t approaches x. Plug in x in t. Then the limit is negative 1 over x squared. Negative 1 over x squared is the derivative of this function, 1 over x. To determine an equation of the tangent line at this point, we need to determine the slope of the tangent line. The slope of the tangent line at this point is derivative at negative 5. Derivative at negative 5 is the slope of the tangent line at this point. Because derivative at x is negative 1 over x squared, I plug in negative 5 in x. Then the derivative is this number. This number is negative 1 over 25. Now, I know the slope of the tangent line, and also I know this point is on the tangent line. Therefore, I can write down the equation of the tangent line by using the point slope formula. By this formula, y minus y1. y1 is the y coordinate of this point. It is function value at negative 5. Is equal to slope. Slope is negative 1 over 25. Parenthesis x minus x1. x1 is the x coordinate of this point. Function value at negative 5 is 1 over negative 5. Simplify this equation, then we get this equation. From this equation, it's easy to see that we have this equation. And this equation is the answer to the second question of this example. Topic 2, other derivative notation. A derivative is usually denoted by prime. The prime notation is popular. A second popular notation for derivative is d over dx. Here, all the notations mean the same thing, the derivative of the function f. Because y is equal to f of x, f prime of x is equal to y prime, and dy over dx is equal to df of x over dx. We will see some examples about the d over dx notation in topic 3, the next topic. Topic 3, more examples. Example 1, let function f be the square root of x. Part A, compute the derivative on function f. Then find the derivative at 1. This notation means compute the derivative on the function f first. After getting the derivative, plug in 1 in x. And find the derivative at 2. State the domain of this function. Part B, find an equation of the tangent line to the graph of the function f at this point. This point is on the graph of function f because the y-coordinate 2 is the function value at the x-coordinate 4. Plug in 4 into the function. Square root of 4 is 2. Solution to part A. For the derivative at x, we have two formulas. Let me use this second formula to compute the derivative. By this formula, I have this equation. In this equation, replace all the x by x plus h. Then f of x plus h is square root of x plus h. F of x is square root of x. So I have this equation. To find this limit, I can use direct substitution. H approaches 0. Plug in 0 in h. But then I will have square root of x minus square root of x, 0. And the denominator is also 0. So 0 over 0, I cannot tell the limit. To find this limit, I need to simplify this fraction. Because the numerator is a square root minus a square root, I use algebraic conjugate to simplify this fraction. That is, I use this formula. I use a square, the square, and b square to cancel the square root. View the numerator as a minus b. Then I multiply the numerator by a plus b and the denominator by a plus b. A plus b over a plus b is 1. I just multiply this fraction by 1 and I didn't change this fraction. a fraction times a fraction is the numerator times the numerator and the denominator times the denominator. So I have this equation. Now apply this formula to this product. I then get this equation. Cancel the square root and square. The square root and the square, I have this equation. Cancel x, then cancel h. I have this equation. To find this limit, h is approaching 0. Plug in 0 in h, then the limit is 1/2 times square root of x. This is the derivative of the function at x. After we get the derivative at x, plug in 1 in x, then the derivative of the function at 1 is 1/2 times square root of 1. It is 1/2. Plug in 2 in x, then derivative of the function at 2 is 1/2 square root of 2. The domain of this function is any positive number. If you try 0, then your calculator says that not computable, 1/0. If you plug in a negative number in x, not computable. So this function, the domain is from 0 to infinity, not including 0. Part B. Find an equation of the tangent line to the graph of the function f at this point. To find an equation, we need to determine the slope of the tangent line. The slope of the tangent line is the derivative of this function at point 4. This is the derivative of the function at x. So at point 4, plug in 4 in x, then we get derivative at 4 is this number. This number is 1/4. After we get the slope of the tangent line, and because we know this point is on the tangent line, so we can write down the equation by the point slope formula. Y minus y1, y1 is 2, is equal to slope 1/4, parenthesis x minus x1, x1 is 4. This is the equation of the tangent line. Simplify it, then we get this equation. This is the answer to part B. Example 2. Each of these two limits represents the derivative of some function f at some point A. State such a function f and the point A in each case. For the derivative at the point A, the formulas are these two equations. Now, solution to part A. We need to determine a function f and a point A such that the derivative of the function at point A is this limit. To find function f and the point A, compare this limit with this formula. Then A is 1 and the function f is x to the fourth plus x. And function value at a is 2. So the answer is a is 1 and the function f is this function. Solution to part B. We need to determine a function f and a point a such that the derivative of the function at the point a is this limit. To find the function f at the point a, this time I compare this limit with the second formula here. By comparing this equation and this equation, I can see that f of a is 2. F of a plus h is the fourth root of 16 plus h. So we have these two equations. Now, from this equation, the left side is a plus h, the right side 16 plus h. Therefore, a is 16. A is 16. Plug in 16 in a, then we have this equation. Now, set x to be 16 plus h. H is a variable. X is a variable. Then this equation becomes f of x is equal to the fourth root of x. So the conclusion to part B is the function is the fourth root of x, and the point A is 16. Example 3. Let f be this function. This function is defined piece by piece. The a here is some number. Now, determine a value of a so that the derivative of the function f at the point 1 exists. By definition, derivative f1 is this limit. This limit may or may not exist. If Sx approaches 1, this fraction approaches more than one number, then this limit doesn't exist. This is a both-sided limit. X can approach 1 from the left side, can approach 1 from the right side. The function f is defined differently on the both sides of the point 1. On the left side of the point 1, the function is 2x squared. On the right side of the point 1, the function is ax minus 2. They are different. So instead of computing this both-sided limit, I compute the left-hand side limit and the right-hand side limit respectively. This is the left-hand side limit at the point 1. X approaches 1 from the left side. X approaches 1 from the left side, so x is less than 1. In this case, the function f is 2 times x squared. Function value f1, plug in 1 in x, then function value f1 is 2 times 1 squared. It is 2. So we have this equation. Now, to find this limit, direct substitution. Plug in 1 in x, but then we have 0 over 0. We cannot tell the limit. To find this limit, simplify the function. Factor the number 2 out, then I have this equation. Then factor x squared minus 1 I have this equation. Cancel x minus 1, then I get this equation. Now to find this limit, plug in 1 in x, then the limit is 4. Now compute the right-hand side limit at the point 1. X approaches 1 from the right side. When x approaches 1 from the right side, x is greater than 1. But when x is greater than 1, the function is ax minus 2. Function value at 1 is 2. Therefore, I have this equation. Simplify the numerator a little bit, then I have this equation. The value of this limit depends on the value of a. If a is 4, then the limit is this limit. Take out the number 4 and cancel x minus 1. Then the limit is this limit. This limit is 4. If a is not equal to 4, then this limit is infinity. How to see it is infinity? Plug the number 1 in x. Then the limit is this number. This number is a minus 4 divided by 0. Now, a is not equal to 4. So a minus 4 is a non-zero number. Non-zero number divided by 0 is infinity, either positive or negative. Now, we can make conclusion. Derivative at 1 x6. Derivative is a both-sided limit. The both-sided limit x6 only when a is 4. When a is not equal to 4, left-hand side limit is 4. Right-hand side limit is infinity. They are different. So in the case when a is not equal to 4, derivative at 1 doesn't exist.